So we are going to just start by finding limits of graphs and then finding limits of functions that don't have a graph. When they talk about limit, they're actually talking about what is happening to the y as the x does something, all right? Not necessarily what it's defined at. So if we want to know what y equals, we're going to plug in our x and solve for y. That's how we do it, right? But if we're looking for limit, then we don't necessarily care what happens when x equals that number. We want to know what's happening as x approaches that number. There's a difference, all right? When x actually equals the number, you would just plug it in and solve for y. The limit is what happens as it actually approaches it. And it's okay if it's not actually defined at that specific point. So look at the graph they've given us. This graph looks like it would just be a y equals mx plus b line, right? Looks like just a standard line. All right, we would standardly have just a slope and a y-intercept and all that. They want to know the limit as x is getting really, really close to c. So first of all, let's look and see where we are. This is c right here, all right? They want to know the limit as it gets to c. Well, what are they asking for? Limit is always referring to your y value. What is your y doing? And so we're going to say, well, x is getting close to c, and x is getting close to c. What is y doing as that happens? All right? Well, on the left-hand side, y looks like it's going down, right? And it's approaching this number right here, whatever this number is. Everybody see that? On the right-hand side, if I were to travel the x's and head towards that x, y is going up. But what you can tell is they are approaching the same value, that hole right there. Now, according to what we just did, if I were to plug in the x, I would actually have a problem. How do I know I would have a problem if I plugged this value in right here? What tells me that I would have a problem? What in that picture tells me that if I were to actually plug this number right here in, I would have an issue? Why do I know that? So we just did ones where you were looking for problems, right? So this tells me that that number would actually cause a 0 in the denominator. Specifically, a 0 that I could cancel out somewhere, right? So even though it at that exact point doesn't actually have an answer, it actually has a hole, this thing can still have a limit. Because all I'm asking for with limit is what is y going towards? That is what limit means. What number is it going towards? I don't care what actually happens at the point itself necessarily. I care about what's happening as it moves towards that point. And in this case, it is moving towards this right here. So my limit value could actually be the hole itself. That's the limit because that's what it's approaching. It doesn't mean that's what the answer is if you were to plug it in. It means that's what y is moving towards. So let's look at these examples. The example we're about to do is just estimating it because it's on a graph. And so you're just going to say this is what it looks like is happening, right? Especially if it's a decimal or something. You're not going to be able to give me the exact value. But we're going to look at it. So it says estimate this limit using the graph. All right? Supports your conjecture using the table of values, which we'll look at in just a second. They want the limit as x is moving towards 2. So the first thing you want to do is you want to find 2 for your x value. So my x value of 2 is right here. Everybody see that's my x value of 2? I'm going to draw a vertical line at 2. All right? So it wants to know what I think y is moving towards based on this graph. So I'm going to look at my y values. Now, my y values are my ups and downs of my graph, all right? So I'm just going to follow the graph like I was on a roller coaster when I get to that point. So it starts way up here somewhere in the sky, and it's moving down towards this point right here, right? And I need to check and make sure that it's getting towards that same point as I go the other direction. So if I go the other direction, yeah, it appears to be moving towards that same point. So if I were to guess what that point is, I would guess the limit here is -5. Does everybody see that? That's when this graph approaches and reaches 2.
So wait,
Oh, so it's just
5? So it can be everything on that line but the 5.
Or the 5 could be filled in. Limit is just saying, what does it look like y is moving towards? If I were to track down here, so here y is 0. Everybody see that? Right here y is 0. I'll make it bigger. All right. Right here y is 0. 0, right? Here y is -1. But I'm still not at 2 yet. 2 is way over here, right? Here y is -2, right? Everybody see that? Here y is -3. Here it's -4. Here it's -5. And at this point, it looks like my graph has reached that 2, right?
So could you call that like an equal point where both of them?
The limit piece is telling you what x value you're looking for. Your answer is going to be the y value, okay? The y value is your answer.
Okay. So the answer would be 2.
I'm going to show you one more piece of this. For this particular graph, do I have any problems? So let's look at the function itself. They gave me the function -3x + 1. Are there any problems with that function? Like, is there anything that would cause a hole or an asymptote? Do I have a denominator? No, I don't have a denominator, right? Can you see? I mean, it's -3x + 1. Is there a denominator in that? No. So this is a continuous function. There is no problem in the graph. So anytime you have a continuous function, wherever this guy actually is defined is going to be your limit. All right? So the first way you can find a limit is by plugging it in. If it doesn't cause a problem, you're good to go. So what happens when I plug this in? Y equals -3. They want me to go towards 2 + 1. That was my limit. Since it is a continuous function, your limit will always be the same thing that happens when you plug it in. Always.
So you're saying that we could...
So the problem with this is, what do they want me to approach? Right here, they want me to approach 3. Can I plug it in?
No.
Why not?
Because that would create a C.
We have a problem, right? So let's look at the graph then. First thing I'm going to do is I am going to find 3. Here's my 3 right here. Everybody see that? There's my 3. All right. So then we just want to find out what it's getting close to. It's going up. It looks like it's moving towards 6, right? As we go on the other side, it's moving towards 6. So based on this graph right here, my limit would be 6. So the limit, as x approaches 3 then, is going to be 6. Even though I cannot plug it in, and at 6 is a hole. That's okay, because what y is getting close to is what it's asking for when it asks for limit. It's what y is getting close to. So this is what I've been saying. The limit of the function as x approaches c does not depend on the value of the function at that specific point. This first one is just like the one we just did. If I were to try to move towards c, okay, I will not be able to plug it in because I have a hole there. But if I look at my graph, it's going to that same value, this L, whatever L is, in this case 1. All right? So this is the limit. We're good. Look at this one. Is this graph defined at C? There's a hole in it, but there's a number that is actually part of the graph, this dot. So this number up here looks like 3 is what happens if you actually plug that number in. You would get this number. But that's not the limit, because that's not what y is approaching. Y is still approaching this L right here, this 1. Even though at that point it jumps to another part of the graph. The other part of the graph is not the limit. The limit is what is actually happening here. So you can have this first thing where you have nothing at that point, and that's your limit. You can have this where it's actually defined somewhere else, and this is still your limit. Or you can have a continuous graph like we did on the first one, where it is defined and what is approaching is the same thing. That's also your limit. All 3 of these have the same exact limit, right? They just look differently on the graph. One of them's undefined, one's defined somewhere else, and one is defined at the same point that happens to be your limit. All three of those scenarios could happen as you're given these. All right, because you're just looking for what is approaching. So one of the things about overall limit is they have to be approaching the same thing. If they're approaching two different things, then you don't have an overall limit. All right. An example of this would be, if I were to move this out of the way, if I were to have a graph, right, something like this. And let's say I had a graph that was doing this, right, and then you have a hole and then it jumps. Like let's say we have some sort of jump graph here. All right, this guy would not have an overall limit. If I were to try to say, what's the limit? And actually, let me do this. Let me do it right here. So it's defined everywhere. All right, if I were to try to find this limit, I would be tracking along, right? And I would say, oh, it's approaching this number right here. Whatever this number is. Let's say that's 2. So from the left-hand side, I would say, oh, yeah, it looks like y is going to 2. But then I have a problem, because if I come from the right, it looks like y is approaching 4. This right here, you would tell me, has no overall limit, because they have to be going to the same thing on either side of the number, okay? So when that happens, you would say, nope, there's no overall limit. But there could be one-sided limits. There could be a one-sided limit. And that's what this guy's talking about here. So if you look in your book and you see these one-sided limits, all right? So in order to have an overall limit, they have to be going to the same exact number. So they have to meet in the middle, all right? Even if there's a hole there, from both sides of the number, you have to be approaching the same thing. If they don't have an overall limit, so let's say it's like this, and they're approaching two different things. So this is tracking along, and y looks like it's going to get to 2, right? Right-hand side is tracking along. It looks like it's going to 4. You would say no overall limit, but I can have a left or a right limit. So they could say, well, what about just from the left side? What is y doing? So I'm going to go over here on the left and move towards my number. And I would say, well, from the left, y looks like it's going to 2. That would be the limit from the left. And from the right, it looks like y is moving to 4. That would be the limit from the right. So you can have a left-handed limit and a right-handed limit independently. If those are the same number, you have an overall limit. If they are two different numbers, you just have a left-handed and a right-handed limit. You do not have an overall limit. All right, so what does this look like? So let's say I wanted to do this one right here. Let's say it's C, whatever number that is that I'm looking towards. My left-handed limit would be written like this. The limit as x approaches C from the left, which is denoted with a little negative sign up above the C. Why is it a negative? Well, think about a number line. Which way is negative? Left is negative. Which way is positive? Right is positive, okay? And so if I were to talk about this one, my limit from the left, well, that would be 2. Because from the left side of that graph, I am moving towards 2. You start on the left and you move towards the number, this number being C. What is y when I move towards that number? Y looks like it's moving to 2. Right, the right-handed limit looks exactly the same, but it has, what do you think, above the C? Instead of a minus, it has a plus, right? And for this graph that I just drew, what would the right-handed limit be? Well, if I start on the right and move, it looks like it's moving towards 4. So that would be my right-handed limit. So then you look at these two numbers and say, does it have an overall limit? And you would say no. Overall limit, which doesn't have the plus or minus. So it's just limit as x approaches C with no plus or minus. We don't have one. We do not have one. They have to be the same number to have an overall limit. And those are not the same number. So my answer is no overall limit, but I do have a left and a right limit. All right? So visually, it's very easy to see that there is no overall limit, right? If you are given a graph, you can see right away that if I am moving towards 0, so 0 is my axis, you can very quickly see that's not going to have an overall limit, right? Can you see that? One's coming down here and one's coming up there, and we definitely are not going to meet, okay? But it is going to have a left and right. So let's look at the left-hand limit, this one. So the limit as x approaches 0 from the left. What is that limit going to be? It's going to be -2, right? 1, 2. So if I am from the left and I'm moving towards 0, my y value here is going to be -2. Everybody see that? Limit always represents the y value. So this guy is going to be -2. Let's look at from the right. As x approaches 0 from the right, what's happening there? +2, right? And then they ask for overall limit. And you would say, it does not exist. We do not have one. Does not exist. All right? There is no limit overall. Now let's look at this guy. From the left. From the left, what's happening from the left? What's my y value here? 4. All right, from the right, it's actually the same number. So your limit from the right is 4, which means your overall limit is actually going to be 4. And you do have an overall limit for that one. All right? Questions on those? Easy enough? All right. So this particular one wants me to move towards 4. Here's 4 right here. All right? What's happening, though? What's happening at 4? Yeah, it's going up, right? So from the left-hand side, it's asking for overall limit. So from the left-hand side, I'm moving towards what number? Yeah, positive infinity, actually. But what about from the right? Do I have an overall limit then? Yeah, I do. So this is actually an infinite limit. This is unbounded behavior. And so you could actually say that the limit here is just infinity.
Would it be the same thing going down?
You can have a limit as infinity. Now, it's not actually a real number limit because infinity is not a real number, right? It's a representation of a set of numbers. But they're both approaching the same thing. They're approaching infinity. All right? Look at the next one. All right, they want an overall limit. What's happening from the left-hand side? It's approaching what? Negative infinity. What about the right-hand side? So it is going to have a left limit. So as x approaches 0 from the left, it's going to have a limit. As it approaches from the right, it will have one, but it will not have an overall limit. So this particular one will not have an overall limit because they're different. All right, no overall limit. Now there's some ways that you can tell this algebraically. If I just look at 1 over x, all right? If I'm getting towards 0, I'm going to be putting in negative numbers, right? Negative numbers that get really, really tiny. So 1 over -1 over 10. That's going to be -10. 1 over -1 over 100. That's even smaller. That's -100. You can see that that's going to be plummeting, right? From the left-hand side. If I were just plug it in. From the right-hand side, positive 1/10. Well, that's going to be positive 10, right? 1 over 100, which is even smaller, is going to give me... This guy, you can even, without the graph, you can tell that's going to be getting huge in the positive side. So even just looking at the function itself without the graph, you can very often tell what's happening. All right? If this were absolute value, this would actually be approaching the same thing. But it's not absolute value, so it's going to be approaching two different things. So if I'm approaching two different things, I'm not going to have an overall limit, but I'm going to have a left and right. If I'm approaching infinity, unbounded, I'm not going to have an actual number like 1, 2, 3, 4, 5, but I can have a left and right hand limit of infinity. And if it's the same, positive infinity or both negative infinity, that could be my limit at infinity, okay? But there are times when you will not have a limit at all right? You will not have a limit at all, left or right. This one right here is called oscillating. All right, so think about an oscillating fan. What's happening with this is it's literally bouncing back and forth very quickly, all right? It's not a slow and steady wave. It is really a bouncing back and forth. And so if you were to look and see what y is approaching, y would be approaching this, and that would bounce up here, and that would bounce down here, and bounce up there. You're not going to have a limit because y is not approaching anything. It's just continually bouncing back and forth. So you would say no limit. No limit. No limit here at all. When it's oscillating behavior like that, there is no limit.
If it's no limit, what?
And so they've given you kind of a list of things. Overall, this is talking about overall limit. And this particular one, because I'm going to deal with this one right here, is talking about real number limits. All right, real number limits overall. You can have a left and a right potentially, but if they approach a different value, you will not have an overall limit. All right, you will say no limit. You might have a left limit, a right limit, but you will not have an overall limit. All right. If it goes to infinity, it's not going to be a real number. Your limit is going to be either positive or negative infinity if they both approach the same one. All right. But you won't have a real number. Like you can't tell me 5, 6, 7, or 8 for something like that. And if it oscillates, this is also going to be no limit whatsoever. So you would say no limit here at all. Here, you could say maybe x from the right or from the left, but you won't have an overall, so no overall limit. And if it's something like this, your limit's not going to be a real number, it's going to be an infinity. And in order to have an overall, they have to be approaching the same one, either both positive or both negative. If it's not both the same, it's going to be a left and right limit. So limits at infinity. Limits at infinity. This is different than infinite limits, all right? So the answer was infinity with that other one. Here we're plugging in infinity. Like our number is continuously getting bigger, all right? And so it has all these words. So the value approaches a unique number. Then it's that unique number. If it approaches a unique number as it decreases, it's going to be a negative. What you're really looking for with these infinite limits is, does this zero out or does this actually go to infinity? That's basically what you're looking for here. All right, so let's look at these. Let's look at this first one. As x approaches infinity. As x approaches infinity. So this is actually going to tie to our bell work a little bit, but we'll see it. My numerator is getting significantly bigger. Yes? Denominator. My x is my denominator. My numerator is 1. So it's staying exactly the same. All right? So if my top number is staying exactly the same and my bottom number keeps getting bigger, let's start with 10. And then it's going to keep getting bigger. Go to 100. 1,000. What is this the whole number itself? Is it getting smaller or larger? Smaller. 1 over 10,000 is a tiny number, is it not? So if I were to write this in decimal form, we have 0.1, 0.01, 0.001, right? Right? So what do you think that guy's moving towards? Looks like it's moving towards 0, right? You can't really approach infinity from the left so much, but, you know, if you look at it, yeah, it would take a while. If you look here, as x approaches positive infinity, which is this way right here, it is going to get significantly close to 0, right? It's never going to touch 0. It's never going to cross over 0. It's going to get infinitely close to 0, which looks strangely like a horizontal asymptote. Remember what we did at bell work, right? Does it not look like a horizontal asymptote? Yeah, it does. So my denominator here has an exponent that is larger than my numerator, and my limit ended up being that, 0, which matches what I did for bell work with my horizontal asymptotes, shortcuts, right? Everybody see that? That's what's going to happen with infinite limits, by the way. Let's look at this guy. Negative infinity. It's approaching negative infinity. But I'm squaring it. Everybody see that? Is my 3 changing? No. So my numerator is staying exactly the same. My denominator is getting significantly larger. What's going to happen to this piece of it? It's going to move towards what? My numerator is staying the same. My denominator is getting really, really big. What is it moving towards? Moving towards 0. What about my shortcuts? My denominator is bigger than my exponent on my denominator is bigger than my numerator. This guy right here is moving towards 0. Everybody see that? Is this number changing at all if my x changes? Why not?
Because it's 2.
It's 2. It's a constant, hence the term constant, right? There is no x with it. So my 2 is never going to change. This part is going to move towards 0. So what do you think my limit's going to be?
2.
2. My limit's going to be 2 there. Because that first part of it is going to 0 out. My second part is not going to change. And if you look at that graph, that's what it moves towards as it goes to negative infinity. It moves towards positive 2. It doesn't ever touch it. It gets significantly close to it. All right? Go ahead and figure out what this guy is going to be. As x approaches infinity, what's my limit going to be there? Here, this is going to 0 out. The negative 3 is not going to change. Your limit's going to be negative 3.